To identify, quantify, and map Earth's surface features based on their spectral characteristics, you should understand what influences the spectral response patterns. You've learned previously that the imaging spectroscopy sensors measure electromagnetic radiation reflected by the Earth's surface after its interaction with the atmosphere. However, besides the atmospheric effects, an object's geometric reflectance properties are important, namely illumination and viewing geometry as well as surface roughness. In addition to the viewing geometry and incidence angle of the incoming radiation, the reflective properties of an object are primarily linked to its surface characteristics. Smooth surfaces usually cause specular reflection, while rough surfaces cause diffuse reflection. Whether a surface is perceived as rough or smooth depends on the wavelength. In the ideal case of a specular reflector, the angle of reflectance corresponds to the angle of incidence. The ideal case of diffuse reflection is described by a Lambertian surface, which reflects the incoming radiation uniformly in all directions. However, most natural surfaces reflect as a mixture of specular and diffuse reflection. In addition to surface reflection, discontinuities within a material can also lead to backscattering, also called volume reflection, which is always diffuse. Some typical geometric effects that can influence the reflectance in an image are, for example, differential shading, differential scattering, and specular reflection. Differential shading refers to variations in brightness that can result from similar objects being located at different image positions, as the sides of features may be either sunlit or shaded. In such cases, the sensor receives more energy from the sunlit side of a tree than from its shaded side. This is an effect of solar elevation and object height, with increasing influence at low solar angles and compounded by differences in slope and aspect over variable terrain. Differential scattering refers to an effect described previously. Backscatter from molecules and particles in the atmosphere adds light, the so-called path radiance, to the light reflected from ground objects. This effect may vary over image locations due to geometric conditions, and may be small and can be ignored in some analyses, whereas it often results in varied illumination across an image, especially under hazy conditions. Finally, specular reflection represents the extreme in directional reflectance that can completely hinder analysis of the acquired imagery. This effect is sometimes observed over water bodies, as a considerable increase in brightness and even saturated pixels that usually contribute little information about the object involved. Because of their low information content, specular reflections are avoided in most analyses. As Lilsand and colleagues wrote in 2008, the most complete representation of an object's geometric reflectance properties is the bidirectional reflectance distribution function, short BRDF. For example, the reflectance of grain fields differs depending on which direction the sensor is looking from or where the source of radiation is located. The BRDF of a vegetation stand has a forward scattering area and a backward scattering area. Forward scattering is observed against the direction of illumination, and backward scattering with the direction of illumination. Therefore, the reflection in the backward scattering area is always stronger than in the forward scattering area. The BRDF is a very important source of information and enables two main applications. Firstly, it is used to correct viewing and illumination angle effects that often occur in case of multitemporal imaging. On the other hand, characteristic BRDF properties can also be used to better separate classes. Besides these physical influences, the reflective properties of an object are of course also influenced by its chemical characteristics. For example, the reflectance spectra of soils are largely influenced by its organic content and mineral composition, as well as moisture and grain size. Vegetation spectra show effects of species, vitality, or phenology that are linked to moisture and phytopigment contents, and even water is largely influenced by phytopigments. We'll get into the details of that in the next topic.